What you're looking at is a Triad Systems Corporation Model 10 computer for auto parts stores that harkens from the late 70s and early 80s. It was sold to auto parts stores in the United States, Great Britain, and Canada. And I think they were moving into Australia in the late 80s. I used to work for Triad. I was a field service tech, and we were throwing these away when I left the company in 1987. Late 1987 I left. I started in 1981. So I worked on these for 6.5 years, and we have been throwing them away. We're selling them for scrap. Actually, there's about 100 pounds of aluminum in this thing, and so that's where it was going. So I've had it since 1987. It spent most of its time in kind of a damp basement near a wood shop. So time was not very nice to it. It was covered most of the time, but it no longer starts it no longer will start. And if it does start, we won't know if it does, because I don't have a printer and I don't have a display or CRT for it. But it consists of, between my hands here is a controlled data 9427H disk drive. It's got two 14-inch discs. One is removable and one is not. Down below, we have the part that Triad Systems made. Triad made all the software. They developed all the software and everything down here. These are the circuit boards that control the disk drive. They did not make the power supply, but they made the rest of these boards, which I will explain now. These are the boards that comprise the Triad designed and built brains underneath the disk drive. So the disk drive is just storage. Everything else is through these boards made by Triad. All these boards use mostly 74 LS series chips. Some are just 7400, some are 74 S chips. I'm having trouble remembering some of this stuff. This board controls the input and output. It would control, for instance, one CRT and one printer. A typical auto parts store may have 5 CRTs and 2 printers in there. So the more devices you have, the more of these boards you need. And these boards use a Z80A microprocessor and a pair of UARTs. And they communicate. This is the chips down here where the data actually leaves the board. They communicate via RS-232 or RS-422 protocols to the outside world. The peripherals, the printers and the displays, or the printers and the CRTs, are hooked up with just plain old phone wire through phone jacks. It was very easy to hook things up. This is the memory board the computer uses. It's only 64K of RAM. Judging by the number of chips we have on here, these are 4116 chips, or 16K by 1 bit. But judging by the number of chips, a fair number of these are used for error correcting, I would imagine, because it did do error correcting. These are dynamic RAM chips, so they have to be refreshed also. So some of the circuitry is to keep the chips refreshed. This is the PRZ board, the processor board. We got 6 indicator lights. We have a little switch that uses to reboot the machine. We got another Z80A processor. And this is a PROM, so this must be involved in telling the disk drive where to look for the initial boot sequence. This is sort of the gem of the computer. This is what makes it do what it does. This is called an RGU, which means Report Generator Unit. This board does hardware sorting of everything. So when you look up a customer number inside the computer, when you look up a part number of an auto part, a purchase order, you look up anything, the computer has to find it. This board finds it. Other computers used software to find it. Software was slow. This board was fast. There you go. And this is the DKC board. This is a disk controller, so this is the interface between all these other boards and the control data disk drive. Let me find an example of something here. Here we go. Part of our job involved doing what were called engineering change orders. The electrical engineers that Triad had out in Sunnyvale, California is where the company was founded. They designed all this stuff, and they would also occasionally change the circuitry a little bit. So this has had 3 wiring revisions done on it. And it's even got my initials behind here. These tags refer to a specific engineering change order. And those change orders consist of wires. It's 30 gauge wire wrap wire that we would use to make changes on these boards for reliability, or I think in this case it was for compatibility. Looks like in this case we added a chip, so we added a socket in one of these spare pads. Added a socket and installed a 74 LS74, which I think I know what that is, but I'm not even going to guess. A flip-flop? Don't know. Anyway, that's it. What we're looking at here is the carriage assembly that carries the heads. I've removed out of the way the card cage, unplugged the head wires, the head cables. There's 4 of these cables for each read-write erase head. And in the center of the screen is this device. It's called a position transducer. This is half of it. This is the other half. You can't, the back side, the other side of this looks like this. And what that is, it's etched lines on a circuit board that are I believe 5/1000ths of an inch apart. They're vertical lines. They better be vertical. They're so close you really can't see them. But the same thing exists on this piece, on the back side. The same thing is there. Watch what happens when I move the carriage assembly. These 2 transducers will move parallel to each other. As the heads move in and out, as the heads move to further tracks, they count these lines. These transducers can count the near microscopic vertical lines that exist on here. And the disk drive keeps track of those lines, keeps track of those counts, and it knows what track it's over. You can get an idea of what track it's over from the scale on top, right here. That would be roughly track 1. You can't quite see it, but there's numbers on below here. So there's about 411 tracks, I believe, across the whole width of the disk. And they are kept track of by this thing called the position transducer. It counts the lines, it counts the tracks using an electrical property called capacitance, which you've probably heard of if you're watching this. Here we see an aluminum bar. This aluminum bar is attached to the frame down underneath the spindle here. Aluminum bar runs up. Looks like it's got a little rubber cushion. Runs up and it hooks into the position transducer that's fixed, the one that doesn't move. So that bar is attached to the position transducer, which does not move. The bar is made out of the same alloy of aluminum as the disc. Therefore, as the heat changes, if it gets warmer and colder, and that disc expands and contracts, this bar will do the exact same thing. When the bar moves a little, when it gets a little longer by like a 10,000th of an inch, the fixed position transducer can flex out these thin steel flaps here, these mounting plates. When this gets longer, this thing will actually move away from the camera by just a few 10,000ths of an inch, if even that much. And that just makes sure that the heads are always moving to where the track on the disc is, even if the disc expands or contracts a little bit. Let's see, can we see here? We can see one of these ball bearing wheels that mounts on the carriage assembly that rides on this track. You can see the track here. It's shaped like a, whatever that is, trapezoid. There's one of these on the bottom. There's one on the top under here that you can't quite see. Here you can maybe see the edge of it. And there's a total of, I think, 8 wheels, 8 or 6 wheels. There's 4 on the bottom, 1, 2, 3. There's 4 on the bottom. I believe maybe there's only 2 on the top. The most interesting part of the carriage assembly, which is where the heads are mounted, is called the voice coil. We can lift up. I've unscrewed this circuit board. It's called a preamp board. You can tilt it out of the way. And you can see the voice coil here. It looks like it's about 16 gauge wire. That's a coil, like a huge subwoofer, for instance, would have something of that nature. When the heads move, they move like this. These are 2 extremely strong magnets. In fact, they're strong enough to pull a pinball off the playing surface of a pinball machine and smack it into the glass. So you can lift a pinball up to the glass on a pinball machine, move it around and drop it. The proprietor of whatever bar that pinball machine is in may not appreciate that, so it's not always a good idea. But anyway, these are very strong magnets. These are not. And the magnetic field is concentrated in the center, which is how this thing moves. It's I forget what it is. I think it might be 34 volts or thereabout that goes through this voice coil and moving it on the tracks, moving it on the ball bearing wheels to move the heads in and out. This wire goes to what's called the velocity transducer. It's a long tube that is held in by a set screw that goes through the center of the whole thing, through the center of the voice coil, through the center of the pole piece of the magnet here. So the disk drive knows how fast this is moving, and through what I showed you down here earlier, it knows where it's at. And so all it needs to do now is figure out what sector it's at, where around the circumference of the disk the heads are. And that's done by something else. What we see now is the disk drive is turned over on its side. And so you're looking at the bottom of it. In the upper left here, this is the motor which drives the discs. It drives those discs through this fabric belt, which is kept tight by this idler wheel here. These were a source of failure, and so on later iterations of this disk drive they were eliminated, and the motor itself was mounted on a spring-loaded device which kept the belt tight. These are 2 electronic switches which start the motor, start the start winding through the capacitor, and then keep it running with the just the regular winding. You learned earlier how the disk drive always knows what track it's on. And you also learned that it also knows how fast those heads are moving between tracks. The third piece of information it needs is to know what sector it's in. There are 24 sectors on this disk. And so maybe you can see there are little dots on here. This is the bottom side. Remember, the disk is on the top side of this bearing assembly. So the disk drive counts these dots through this transducer here, and it always knows what sector it's on. The drive does this without any software, without any computer, without a microprocessor. It's doing it with just old school dumb gates and latches and flip-flops and such, and it's pretty impressive it can do that, to keep track of where it's at and to provide the timing needed to read the data off the disk. Let's zoom out a little bit. Up here in the upper right, this is the intake of a blower motor, which provides the air for the two disks. It provides pretty clean air, which pressurizes the disk area and keeps dust out of that area. It's just always blowing so hard, dust doesn't really want to go in there. So this is a squirrel cage fan, and it blows down, turns the corner, and goes into this black thing here called an absolute filter. The absolute filter is a HEPA filter, which provides very clean air around the disks. So most of the air out of this goes away from you, up to where the disks are. And the rest of it goes right to left through the bottom of the disk drive's power supply. Now, underneath this cover is, I've honestly never even been in there. I never had any trouble with them in 6.5 years. It's most likely it's a big transformer, and you can see some big stud diodes in there if you look in through the holes. This disk drive has an interesting safety feature to it, that if it senses that the heads are in danger of contacting the disk, such as mainly if the disks should slow down, the sensor underneath that watches and counts the sectors, that sensor will sense that, and the disk drive will protect itself by retracting the heads. It'll just suck them back in very, very quickly. And the way it does that, it lives underneath the cover of the power supply. And inside here, you can see the blue are, I believe, 3 really large capacitors. And as you may know, capacitors store an electrical charge. So if the power should go off, for instance, these are charged up. The machine will know that the power went off. It will activate this relay and send whatever is in here into the voice coil. So if the thing was out here running, moving around, the power goes out, this is what happens. It'll just slam itself back very quickly. These will discharge through the relay into the voice coil and get the heads off the disk. That's actually the problem this unit had the last time I tried to start it up. It wouldn't even start. It would immediately retract the heads after they went out. So let's see, we can look at one other thing here. Let's zoom in on it a little bit. The top of that power supply, which is what develops the DC voltages used on board here. We've got a ribbon cable, we've got some screws I removed, and we've got a connector here under my index fingers. And it's just old school. They are, well, the ones that I recognize the part numbers on there, they're transistors. They're not voltage regulators. And looks like we have there's a temperature sensor here, which keeps track of making sure this stuff doesn't overheat. I suppose that could also shut the machine off. I never saw it happen, but there is a temperature sensor here. Here you can see a big capacitor down underneath. And that's about it. Here you see what was known as the fixed disc, or the lower disc. It's called fixed because the customer would not normally be able to remove it, and the customer could remove the disc that's above this, but not this one. This one had all of the customer's data and all the software on it, all the main software on it. On the top disk was a duplicate copy of the customer's data, along with some additional software. Remember, each disk is only 5 megabytes. So about every 6 months, we would come to the customer site and do preventive maintenance on this machine. It would take probably 90 minutes. First thing we would do, frankly, is to tear it down to this state, remove the disk. Once the disk is removed, you can no longer access any data that's on here, unless you were to somehow, by some miracle, get it in the exact same spot you took it off. So, data and the software is all gone now. We would look at the disk, and I hope you can see right here. I can even feel it with my finger. Looks like a little piece of dirt got between the head and the disc. It didn't damage the disc, but it put some crap on there. You can see it right there. This side isn't too bad. But if I saw this at the customer site, I would get rid of it. Put on a new disc. Clean the disc very thoroughly with what's called Tech Swipes. That was a company that made these little alcohol-infused wipes, and you would just wipe them over the disc. Flip it over. Wipe them over the disc. Screw it all back down. And when you started it back up, you would tell the card cage below this computer, you would flip a switch on it and tell it to don't even bother looking at this disk. Just look at the top disk and boot off that one. So we would boot off the top disk. We would then put the software and the data back on this disk. While this disk was also off, we would clean the heads. You just retract this, or we would extend it out, and we had a plastic wand that you would put a little rubber, put a cloth boot over the end of the plastic wand, spray alcohol on it, and just wipe off the heads real good. We could visibly inspect them and make sure that they didn't have any kind of marks on them. I mentioned earlier about the absolute filter providing air to the disc. The air comes up here. It blowed surprisingly hard. It would blow your hair out of the way if you're standing over this. So it just shot so much air into this area that dirt didn't really want to fall into it. It certainly wasn't hermetically sealed by any means. It was just pressurized to the extent that dirt would stay out. I've reinstalled this black plastic piece, which I think is called the receiver. It's called that because it receives the top disk. In this case, it's called a redundant disk, and it would normally be on this system all the time whenever the customer is using it. And it's called that because the data on it is the exact same data that's on the main disk, so your data is always in 2 spots. It makes it a lot safer that way. Every night, the customer would then put on a different disk. They would change this one. They'd pull it off, they'd put on a different one that was called a security disk. They would then run about, it'd take 5 or 10 minutes. An application they would run, which would then copy all the data to the security disk. They would remove the security disk and take it home, or take it to the bank, or throw it in a safe, or hide it in their car. I don't know. But so then, in that case, it was always on 3 different disk platters, their data. And I never saw a customer lose any data over 6.5 years. So here's the redundant disk. You can probably see it inside, I hope. This disk pack has a set of notches on the bottom. And there's a sensor down here so that the disk drive always knows what sector is coming around to where the heads are. So we'll put this on. People in the know will notice that there's something broken here. This is called a disk pack. A pack lock. This is called a pack lock. And it's meant to keep the disk drive from operating unless this lid is on and fully installed. This one is broke, but there'd be a little piece like this that would come over this and would hold it in place so that you can't remove this while the disk is still spinning. So what we're going to do now is we're going to power it up. And what you're going to hear is the blower motor running. It's forcing clean air over the disks. I have this plug disconnected at the moment. With this plug disconnected, the carriage assembly and the heads, it can no longer move out on its own. I'm going to move it by hand. So we're not going to turn on the motor, which now has the head spinning. Normally these heads would spin for 50 seconds to give the temperature and everything a chance to stabilize, and then the heads would go out and start doing their thing. But with this plug off at the moment, I'm in control of the heads. Okay, here you see at the top of the screen an oscilloscope. The oscilloscope is hooked on to the output of the position transducer. So this is what you're going to see is the signal that the disk drive uses to count what track the heads are over. I'm going to load the heads. They're going to come out onto the disks right now. And the heads do seem to be touching the disc a little bit because you can hear a very faint difference in sound, so I'm not going to leave them out here too long. But you'll see on the oscilloscope, this is the signal generated by the position transducer. Every peak or every valley or whatever, every one of those sine waves denotes that you're moving at one track worth. So I'm moving it slowly back and forth over the discs. Now I've retracted it. I've turned off the disk motor. And turned off the entire disk drive, and now the motor is spinning down, slowing down on its own. People like me that used to work on these, being the impatient people that we were, being in a hurry, we would stick our hands down here and slow down that motor. We would then stick a screwdriver in here, unlock the pack locks, and get this thing off of here a couple minutes quicker than the customer could. Well, I've got the card cage hooked up to the disk drive, and the card cage has been told to boot off the top disk. The disks are spinning, the heads are loaded over the disk, and it seems like it actually did what I asked it to do. It seems to have booted off the top disk. We don't have a printer, we don't have any kind of a CRT or display, so there's no way to really see what's going on. But in my recollection, this is what a reboot looks like off the top disk. That's it. And here we'll retract the heads. We'll shut it off. So that's about as far as this thing's going to go. I'm sorry if I repeated a lot of crap from earlier videos, but I kind of wanted to just sort of get this all cleaned up and give it one last shot. Thank you.